Today we shall study about refraction through prism in ray optics and optical instrument. Figure 1 shows the passage of light through a triangular prism ABC. The angles of incidence and refraction at the first face of AB are I and R1, while the angle of incidence from glass to air at the second face AC is R2, and the angle of refraction or emergence E, the angle between the emergent rays RS and the direction of the incident ray PQ is called the angle of deviation delta, as shown in the figure. In the quadrilateral AQNR, two of angles at the vertices Q and R are right angles. Therefore, the sum of the other angles of the quadrilateral is 180 degree. Angle A plus angle QNR are 180 degree. From the triangle angle UQNR, from the triangle Tribhuj QNR, R1 plus R2 plus QNR बराबर 180 degree. Comparing the two equations, we get R1 plus R2 बराबर A. The total deviation delta is the sum of the deviations at the faces. Delta बराबर I minus R1 plus E minus R2. That is delta बराबर I plus E minus A. Thus the angle of deviation depends upon the angle of incidence. A plot between the angle of deviation and the angle of incidence is shown in figure 2. We can see that any given value of delta except for I बराबर E corresponds to two values I and hence of E. This in fact is expected from the symmetry of I and E. It means delta remains the same if I and E are interchanged. Physically, this is related to the fact that the path of ray in figure 1 can be traced back, resulting in the same angle of deviation at the minimum deviation dm. The refracted ray inside the prism becomes parallel to its base. We have delta बराबर dm, I बराबर E, which implies R1 बराबर R2, इसलिए 2R बराबर A और R बराबर A by 2. In the same way, dm बराबर 2I minus A और I बराबर A plus dm by 2. The refractive index of prism N2 1 बराबर N2 बटा N1 बराबर sin A plus dm by 2 बटा sin A by 2 for a small angle prism. It means a thin prism dm is also very small, and we get N2 बराबर sin A plus dm by 2 बटा sin A by 2 बराबर A plus dm by 2 बटा A by 2 और dm बराबर N2 minus 1 into A. Thin prism do not deviate light much. Now, dispersion of a prism as shown in figure 1. The white light is dispersed into different colors of light as shown in figure 1. It has been known for a long time that when a narrow beam of sunlight, usually called white light, is incident on a glass prism, the emergent light is seen to be consisting of several colors. There is actually a continuous variation of color, but broadly the different colors that appear in sequence are violet, indigo, blue, green, yellow, orange and red, given by the acronym BIBG/UR VBOR. The red light bends the least, while the violet light bends the most. The phenomenon of splitting of light into different colors is known as dispersion. The pattern of color components of light is called the spectrum of light. The word spectrum is now used in a much more general sense. The electromagnetic spectrum over the large range of wavelengths from gamma rays to radio waves, of which the spectrum of light, visible spectrum, is only a small part. Though the reason for appearance of a spectrum is now common knowledge, it was a matter of much debate in the history of physics. In a classic experiment known for its simplicity but great significance, Isaac Newton settled the issue once for all. He put another similar prism but in an inverted position and let the emergent beam from the first prism fall on the second prism in figure 2. The resulting emergent beam was found to be white light. The explanation was clear. The first prism splits the white light into its component colors, while the inverted prism recombines them to give white light. Thus, white light itself consists of light of different colors which are separated by the prism. It must be understood that here that a ray of light as defined mathematically does not exist. An actual ray is really a beam of many rays of light. Each ray splits into component colors when it enters the glass prism. When those colored rays come out on the other side, they again produce a white beam. We now know that color is associated with wavelength of light. In the visible spectrum, red light is at the long wavelength near about 700 nanometer, while the violet light is at the short wavelength 400 nanometer. Dispersion takes place because the refractive index of medium for different wavelengths or color is different. For example, the bending of red component of white light is least, violet is most for violet. Equivalently, red light travels faster than violet in a glass prism. Table 1 is given below. Violet wavelength 396.1 meter, blue 486.1, yellow 589.3, and red wavelength is more, say 656.3. The chromed glass 1.533, refractive index 1.523, 1.517, 1.51. Flint glass 1.63, 1.639, 1.627, 1.62.